Yeah, record started. So good afternoon. So today we are going to continue with microscope related to the electron microscope. So last two classes, I think we discussed about what is scanning electron microscope and uh, the basic principles, application, and some examples how we can get more details about the images and everything. Um, Maybe later, if we have time more, then I will show other informations related to how we can get different signals, and also what kind of informations we are going to get it through this apart from the structure. So the scanning electron microscope, as we discussed, that it is important, and the informations which you are getting from the scanning electron microscope, that does not get it from the light microscope. So the main two reason is, one is the resolution, high magnification. That is most two important things. So how it is possible the high resolution with the higher magnification is because the light source is electron, and also the electromagnetic lenses and other vacuum, that all together which improves the quality of your images. Also, in the light microscope, we know that we get a lot of basic informations for diagnostic purpose, but that is not sufficient to go in details about any given samples. So that's why we chose that the electron microscope plays an important role in advance the imaging. So now today we are going to talk about a different microscope technique that is called a transmission electron microscope. So the scanning electron microscope, you can just compare with stereo microscopy in light microscopy. So the stereo microscopy, you can see one lens, on objective lens, you can see the surface of any samples. A larger samples, it does not need sectioning or things. Just you wanted to see how the surface looks. That is a stereo microscope. So similar function is the scanning electron microscope. The electrons does not penetrate the samples. Instead of the penetrating the sample, it is interact with the sample and bounce back. So that's why you will get the surface images. Similarly, the stereo microscope, you get only the imaging, the surface, because the light source is only on the top. So similarly, the transmission electron microscope, which is like a typical light microscope, when you go for cross section or transverse sections, and the light source is penetrating your sample so that you will see the structure of the cells. Similarly, the transmission electron microscope is also the electron, instead of bounce back, it will penetrate, the electrons penetrating your samples, so that you will see the internal structure. So that is the basics of transmission electron microscope. Here also the electron is the light source, like similarly in the scanning electron microscope. So here the important is, in the light microscope, the highest magnification is 1,000 to 1,500 magnification. So you can see the structures of cells and other things, but you cannot able to see the organelles inside the cells. So if you wanted to see all these organelles, it has to go for higher magnification. That means because each organelle is a micron thickness or nanometer thickness size, so that you will have a more magnification. So how we can able to see all this is a transmission electron microscope, because it has a magnification. Now it is even more, close to millions, 1,000 times, millions of, times higher magnification. Also very fine, detailed structure like ultra structural details. You will get it from the transmission electron microscope. So here you can use only like processed cells, not like a light microscope. You can see live cells, whereas here you have to process your cells. That's also it's a lot of process, not like a light microscopy. So the advantage is over the light microscopy is high magnification and high resolution. That is important as scanning electron microscope. But this is, the processing is take a longer time and a complex process, but the techniques are largely standardized. So it requires, expertise to, detailed structure, and if there is any changes of ultrastructure, you need to interpret the data. You need to interpret the structure so that you will be able to understand further, because the changes of cell types, we have to find out what is that really. So you need an expertise, for to understand the structural changes. Also, then as we see, it's a you will get ultrastructural details, and also only we can be able to see processing samples. So even though we are getting a lot of advantages and other things, the equipment is so expensive, because the instrument itself, it's many components and accessories it require, and because it require vacuum, it need water cooler, and also liquid nitrogen to cool down the samples, and high voltage connection is required, and then ultra microtome and ultra cryomicrotome. There are a lot of accessories it's required to use the equipment. Also, the process is also taking a longer time when compared to the light microscopy. So small samples, which leads to possible sampling error and misinterpretation. So because here you are going to use a very small piece, 1 mm or less than 2 mm, 3 mm size, a small piece of cells to process. So the advantage is, you are going to see detailed ultrastructural changes, but the disadvantage is, if you really wanted to study about any organ, for any changes, that means you cannot process the whole organ or partial. You are going to use a small piece of cells from the organs. So that does not represent the whole organs. So how do you then, overcome with this? Because when you collect biopsy or samples, it should be represent the area of your samples. But here, you will get a lot of other, different cell types. So how do you able to, confirm that the cells are representing how far it is, changes and things, is multiple sampling. You will collect multiple different places within the area of, suspected cells, organs, then you can collect this, tissues and process, and then you will understand, at largely what is going on with this. So optimum tissue preparation requires a special fixative and processing. So as I said that, it takes a longer time, many chemicals, which is expensive and also carcinogenic, complex process, so that, it takes very, very tough if you are not aware of the process. Also, all this, you need a experience to process this, and also interpreting the results, as mentioned before, that how it looks, how it nucleus, but due to some changes, that may be also the structure change, but that changes, you need to know that the changed structure of that mitochondria is mitochondria. You cannot interpret it differently. That means your data is invalid. So these are all some drawbacks, even though we have a lot of advantages and other things. But nowadays, because of the standardized technique, protocol, and expertise, we can overcome all these problems. So the major use of the TEM, you can use this for any diseases, not limited to few of them. So it doesn't matter, the instrument does not tell you, what tissue sample can analyze. So any sample, biological samples, you can process, taking sections, and you can see under the transmission electron microscope. So some of them are diseases, renal, different type of tumors, malignancies, infectious disease, muscular, diseases, different type of, dermatal diseases, and other diseases. You can able to process your samples. So this is a typical, transmission electron microscope is a diagrammatic representation. That is, imagine that this is the, tungsten filament that is generate the source of electron that generate the electrons. So once it generates the electrons, it passes through the condenser lens. So the condenser lens will conduct the, condense the electrons into a small, piece, and, a narrow path. Then, all the electrons together, and it will go through the objective lens, and then projective lens, and then it penetrate your samples. Your sample is here, and once it penetrates, and a projector lens, and then you can see the image. Here it is fluorescent screen. You can see the images here, and then you can we have a eyepiece in the microscope. You can visualize the structure, and also we have like digitalized imaging center. You can see the images. So yeah, typical, this is like a electron source. Similarly, the scanning electron microscope, condenser lens, objective lens, projector lens. These are all the three lenses is important to control the path of the electrons, and it is so it is improve the quality of your images. So the basic transmission electron microscope is to project a magnified image of the specimen onto a fluorescent screen, where it can be viewed by the operator. So how we can able to calculate the images? So nowadays, everything is computerized, digitalized. Just one button, when you click, it will shows you what is the, magnification of your sample when you visualize. So when you go for further, you can magnify. It will tells you how many times you are increasing the magnification. But the mathematical formula, how we determine the calculation of of the magnification of your samples. So the total magnification in the electron microscope is a combination of the magnification from the objective lens times the magnification of the intermediate lens times the magnification of the projector lens. There are three lenses plays important role: um, objective lens, intermediate lens, and the projector lens, which each of which is capable of approximately 100x. So that is the your total magnification. That is objective times and intermediate lens times and projector lens times. So that is equal total your magnification. So already we discussed about the the reason why you wanted to emphasize more on the magnification. So the magnification is because we took a small piece of a sample processing and you are taking sections, and for example you are imaging when you look at them under the microscope at the lower magnification you cannot see anything other than just the structure. But when you go up, increasing the magnification, you will get started to see the internal organs. So it depends on the size of the organs. When you increase more and more, then the lowest, smallest organs will also show. So at every time when you, if it is bigger, you can see in 100,000 times magnification. If it is 200,000 times, maybe Golgi complex. Or, similarly, when you different magnification, you will see a different, it's all depends on how small the organelles. So that doesn't mean that when you see visualize at 300,000 times of magnification, when you take a photo and see, clear, structure of that particular organelles, but that doesn't mean that is the real magnification of that organelles. But because we wanted to visualize that one, we magnify this many times so that we can tell that the scientific community or whoever wants to see this is the organelles. When we increase this magnification up to 300,000 times, so this organelles is a magnification of 300 times. So that is how we can convey this information to others so that they will understand. So when you compare this organelle, this is for example healthy, you wanted to compare this with the other any infections or cancer cells, maybe that is looks like a same 300,000 times magnification that gives you very small area of images you can able to see when compared to the healthy one. So if you wanted to get detail like the healthy one, maybe the cancer cells, the organ, maybe if you increase instead of 300,000 times, you can go for 400,000 times. Now you can see same size of this. So that means it does not mean that the both are same. Okay, when you side by side, when you if you are not telling anyone that this is we took 300,000 times magnification, this is took 400,000 times magnification, if you are not telling to them, they don't know, because it looks like both are at the same size. But at the same sense, if you wanted to bring this to the healthy, we increased 100 times more. So that way we can tell that this, because due to this, malignancies or infections or any other, problem, that organelles is size is reduced. So you have to convey that, to see the structure of that organelles. So you increased more than the healthy one. So these kind of examples, I'm telling why you need to know the magnification. So, like I don't want to go for details about, what are all the parts and each components. For exam point of view, no need to read all these, but you basically understand how small, parts we are using, but your images is increased like 500,000 times, 600,000 times magnification to see things. So, as mentioned, the smaller pieces, we take a ultra microtome cut. And when you look at this is the area, to cover, hold your samples. So here only you placed the grid, that is a supporting material. We'll detail the latter so that you can lock this. And this is transmission electron microscope, the sample holder. You can insert that into a electron gun. So, that would be right away the image. So this is a specimen holder for transmission electron microscope. So, our important goal for this specimen preparation is observe specimen near natural state as possible. Already we discussed this. Our first goal is to preservation. Also, we have to preserve as many features as possible. Also, when you process the samples, there are a lot of chances to get artifacts or loss or additional information you are going to get due to contamination or electron dense particles, due to precipitation of any chemicals. Due to several reasons, the factors affect the quality of your images. Also, we have to provide, environment for the sample to, hold the heat generated by the electron microscope. So some features is important, and the goal is to preserve the samples and keep them ready and process without any artifacts and avoid, tolerance of heat. These are all the basic, we need to consider when you process your sample. So what are all the things we need to consider this? One is that the high vacuum it requires. As we mentioned that, the high vacuum is required, and holding this, samples is also important. So we will talk about the supporting material which hold your samples. Also, intense heat from beam, because the electrons which emitted, and it also not just bounce back, but it is penetrating your samples, so that it will give, the thermal damage to your samples. So that also we have to consider. And also the depth of electron penetration, how much electron should penetrate. That is also important, that is need to be considered. So once you fix the samples, here also the same how we are fixing the samples for the scanning electron microscope. Here also the first is you have to fix the samples with the glutaraldehyde. So that is the primary fixatives for electron microscope. So as we discussed earlier that the glutaraldehyde does not preserve all the features of samples. Some of them which could not be able to fix. So how do we fix the remaining which does not fixed? So once we fix a sample with glutaraldehyde 1 to 4%, then you can post fix with osmium tetroxide. So the osmium tetroxide is we fix the samples, those who are already not preserved by the glutaraldehyde. So if you use the primary fixatives and post fixatives combinedly, then you can um, uh, preserve the most of the features of the samples. So electron microscope, especially with the transmission electron, primary fixation and post fixation, that is two is important. So once you fix your samples, the next step is, as always discussed, is the dehydration. So each and every microscope, the basic principles is you remove the water content so that the subsequent steps will be processed without interfere with the water. And there are each and every microscope, there are some specific reason also we discussed. So here also we are, going to discuss about a common dehydration process specifically for a transmission electron microscope, how it is possible. So water incompatible with conditions inside an electron column. That's one of the reason we wanted to dehydrate the sample. The water incompatible with the conditions inside the electron column. Also, the most of the materials used to infiltrate and embedding the specimens prior to ultra-thin sectioning are all hydrophobic. So that is another reason also we wanted to, dehydrate the sample. Also, the tissue is transferred through a series of organic solvents, which increasing the concentration. That is the goal. So, how do we dehydrate this sample? Is increasing concentration of either ethanol or acetone. So the water content So the water content is slowly reduced to the point that the tissue is 100% solvent and thus completely dehydrated. So how do you say that your sample is completely dehydrated? That is, if you replace the concentration of the ethanol or acetone in a increasing concentration, then at one point you will bring that into 100% solvent. That means the most of the water is released from the samples, and now your sample is fully compatible with the solvents. So that is, you can call it this, it's a completely dehydrated your sample. So after you dehydrate the sample, the important in for transmission electron microscope is to hold your sample. So we discussed that in light microscopy, the paraffin is to hold your samples, and also it helps to take a sections of your tissue samples. Also, the liquid nitrogen, if you fix with samples, liquid nitrogen fixation and OCT medium, that is your supporting material for cryosectioning. Similarly, the scanning electron microscope, the stub to hold your sample. And also to support your samples is coating your sample with either carbon or gold coat particles. Similarly, here in the transmission electron microscope, the stabilization is very, very important and hold your samples and mounting your samples. So the fixation, after the fixation and dehydration, to stabilize your samples, to hold your samples is we can embedding your material in the resin. So we will discuss about what is the resin and what are all the different type of resin that we can use to process your sample. So this cutting is very, very important. Here cutting means it's a sectioning. So in the light microscopy, we take a section using a paraffin microtome or cryomicrotome, that is a 5 to 10 micron. So that's why we called it this microtome. The paraffin microtome, name it is just because the sample is, embedding material is a paraffin. So we take a sections and the paraffin microtome. It's a cryomicrotome because the cryo, it is the microtome, taking sections your material in the below 0 degree. So similarly here, we have to take a sections, we call it is ultra microtome. The ultra microtome is, we are taking a sections in nanometer thickness level. So you can imagine that the compare with the light microscopy, that is my light microscopy is the micrometer thickness, and whereas here nanometer thickness. So that's why we called it is ultra microtome. So the mounting, that is already we discussed in the scanning electron microscope. Another one is, staining for the process. We will discuss about the detailed protocol. The staining here also important. As we mentioned that previously, that electron microscopy is not producing any color image, but it is black and white. Here we are saying is a staining. The staining means we are staining with the heavy metals like uranyl acetate and lead citrate. These two, you can stain the samples so that you will get better brightness and contrast. So this is basic, protocol for the, transmission electron microscope. So first is you can fix the samples to 1 to 3% glyceraldehyde for 1 to 2 hours or overnight or week when you put them into the cold room. Then you can wash thoroughly, the samples to remove, the glyceraldehyde. Wash it several times with the PBS and then transfer that to new tube and now add the 1% of post fixation of osmium tetroxide. So the osmium tetroxide you can fix it's 1% and for 1 hour. Then, at this stage, the sample turn into black or brown due to the osmium tetroxide interact with the samples and oxidized in the air so that you can see these samples turn into black or brown. At the same time, this will gives you hardness to the samples, so that it will help you when we are taking the sections. Okay, so that is the dual purpose of the incubate the osmium, samples with osmium tetroxide. It's not only fix your samples, but also it gives you a strength, hardness to the samples, and also turn into black, then you will easily to see the samples. So then wash that is thoroughly with the PBS again. So the next is it is dehydration process. So always when you do dehydrate from 25 to 50, 50 to 75, 75 to 100, you can replace your samples to this concentration, but you should not wash in between, the process, because your goal is to completely remove the water. So if you lower concentration, if you start with the 25%, wash it and then transfer to 50% and then 75% and 100%. So this is each and every steps, at least you have to leave it for 15 to 30 minutes. It depends on the samples and the investigators. You can, things, but basically it is a 15 to 30 minutes. You can degated the samples each steps with to room temperature. Also, the samples are immersed in 2 changes of propylene oxide for 10 to 15 minutes. So the next step is infiltration. So, as we mentioned earlier, that we are going to, put them in the resin. That is your supporting material. It's very viscous at the room temp, viscous before it polymerize. Once it polymerize, it will become very hard. So, because of the viscous nature of this resin, you need to facilitate this resin infiltrate into your samples. So, for that reason, we use propylene oxide. But some investigators, they are not using propylene oxide due to this carcinogenic nature. So what they do is directly, after dehydration, they go for embedding. So the fresh propylene oxide add to an equal volume of freshly prepared resin. So the resin is, the Araldite or Spur, that's a company name, with the accelerator, that is DMP 30. So here, when you have a sample cut into small pieces, you fix your samples with the glutaraldehyde, post fix with osmium tetroxide and dehydrate your samples. So now you have put them into the propylene oxide. If you are not put them in the propylene oxide, add to the directly, the resin to the ethanol 100%. So the resin, when you have add the accelerator chemical, that is a DMP 30, should also add. So what this do is it will be accelerating the infiltration of the resin into the samples. So that's why we add the accelerator. Also, mix well for 1 hour and changes to, different concentration. So start with 25%, 50%, 75%, and 100%. Similarly, how we processed in the dehydration. So at 100%, you completely, the resin is 100%. So that means your sample completely infiltrate into the resins. So your resin is infiltrated into your sample and it will be ready to go for polymerization. So this is, the very, very important process. Then only you will take ultra micro sectioning. So, this. So once you done with this, the next step is you need a, mold or, anything to hold these samples, right? So fill a clean, dry beam capsules, like a, tablet capsule, you remember, that is, or flat, embedding molds. So what we do is we fill the, mold or the capsule with this resin. And then you take the samples, the processed samples, put them onto the resin. So what it should be do is when you go for polymerization, we can do several different types. One is 3 nights. So the polymerization is nothing but, cured. So when you add the accelerators and, plasticizer, I will give you, so this will, hardener, DDSA is a hardener. So these are all, along with the resin, the mixture should be DDSA, that is gives you the, during the polymerization, will the resin become hard. The DMP, to accelerate this process. So when you do the polymerization overnight, first night you should be 35, second night should be 45, the third night should be 60 degrees centigrade. So once like the satisfactory results have been obtained overnight at 60 degrees centigrade, but the 3-stage cure is preferred. So two methods, one is a 3-night, or if you wanted to go for one night, it should be 60 degrees centigrade. So this is a combination of the resin mixture. The resin mixture is, semi-viscous, and the DDSA and the accelerator, when you add to them and, do this during the polymerization, it react with this and now it become solid. It's hard. So next week, I will show you, in the picture, what are all the looks like and everything. So the acrylics, that is the different type of resin we can use for this. Methyl, butyl methacrystals, acrylic, plexiglass, or epoxies like Ippon, Araldite, Coitol, the spur. For most general work, we use this type of resins. Rarely we use polycarbonates. The most commonly used components for the processing the samples is resin, hardener, plasticizer, accelerator. So the hardener, when you add DDSA, once during the polymerization, it gives you hardness of the resin. The plasticizer is, it helps maintain the plasticizer. So then only you can take a sections. If it's too hard, it will brittle. If it is too plasticizer, that is also cannot be able to take a sections. But optimal, important. The accelerator is to plasticizer, hardener, and resin all together. It help to accelerate the process or curings during the polymerization. So here, like this is what the process after. This is a capsule. When you have a capsule, then this is what after we complete the polymerization, and this is a flat folder mold. You can see that. Look at this, the black. This is our sample, and here also the edge we have the samples. It's the black is a sample because of the osmium tetroxide we incubate so that it turn into black. So the infiltration, as we discussed in this, is the resin solvent mixture, increasing concentration, that is bring into 100% resin. So either you can use a propylene oxide or ethanol, this combination. 100% reached, it should be changed twice and make sure all the either propylene oxide or ethanol or acetone is completely evaporated. The polymerization, as we discussed, that 3 days curing or 1 day at 60 degree. The third option is UV. Cross is done to avoid heat of polymerization, because if it is a 60 degree heat, that will affect the quality of your samples, so that if there is any sensitive to heat, the samples we can go for UV at a low temperature. This will be help to cure this during the polymerization. So embedding and sectioning. So embedding, that is what we discussed, that after infiltration, the embedding, that is to hold your samples. The purpose of that, the resin, is requirements for cutting any material into ultra thin sections. Also, which gives you, the biologicals tend to be soft. The tissue is always a soft, some things. Inducing hardness in them gives them the mechanical support when you take a section. Also, due to, if you are working on freezing, cryofixation, then that is a different things. So the plasticity is important, as I discussed, just said, is a resiliency as opposed to brittleness. So now, similarly, we discussed about the cryo sectioning. Here also ultra cryo section. That is also, if you process liquid nitrogen, then you can go for ultra things. But it is technically demanding and it requires expensive specialized equipments. Also, the ultra structural preservation often poor due to freezing artifacts. Also, usually done only when tissue cannot be exposed to chemical fixatives, as in some immunolabeling analytical work. So the embedment is the tissue infiltrated with a resin which is polymerized by heat or chemicals or UV. So which also provides a support to section infiltrated tissue about 40 nanometer minimum. So that is what, when you take a section, it is, if you go for 40 nanometer, then only you will see detailed structure of organelles. So the infiltration is limited. The specimens can be no more than a few millimeter thickness. Also, it required thinness of the sample and the friction during cutting limits the section size about 1 millimeter maximum. So, how already you are taking samples very small piece, but when you take a sections, that is also very, very small. If you are going to be using a small sample, then your results will be improving a lot when compared to little larger samples. So cutting is very, very important. So here, as mentioned earlier, that is the ultra microtome, because we are cutting is nanometer thickness. So there are different microtomes is available. It's a mechanical or thermal advance. Also the ultra microtome knives, which is, here we use a diamond knife, because, in the glass knife, you cannot able to take ultra thin section. So we have to go for a diamond knife. So that is, the diamond knife is very expensive, and the cutting edge, the diamond cutting size is 1.5 to 6 mm. This is, we call it as boat, and the edge, we have a small piece that is 1.5 to 6 mm cutting edge is the diamond knife. So, both use water to support and to lubricate the section as it is cut. So when we have to fill this boat with water. So once it cuts by diamond knife, the cutting material will be floating on the water. Then from the water, you can pick the samples for analyze. So some components, like tools is very, very important. One is, syringe, loop. The loop will help you to picking up the sections from on the floating on the water. Also, syringe will help you, the trough, adjusting the water level. Here also we use eyelash, that is help you to, manipulate the sections on the water. So there are, you can imagine that one single eyelash that will manipulate your section, means you imagine that how small the section should be. So you cannot see the sections of cutting that is floating on the water with your naked eye. It has to be seen through the microscope. Then only you can see sections, because it is nanometer thickness level. you are taking sections. So the microtome is, taking a sections with the help of diamond knife. So we know that, ultra thin sections, and we use, we equipped, microtome, and, what are all the factors which influence when you take a sections? Also the processing. So embedment. So the proper infiltration is important. If you are not properly infiltrate your sample, then it is very tough to take a sections. The next step is the polymerization. If you are not to polymerize this, if it is too soft or too brittle, hard, that won't be possible to take a sections. Knife. The quality of knife is also important. It should not be damaged the edges. It will give you impression, and also sharpness. It should not contaminate, because very often it will be possible. So that also we can, and also there should not be a scratches. Also the compressions, the life, lines perpendicular to the direction of cuts, micro grooves, that's also not good. In their options, the knife edge will appear as a bright line under a dissecting scopes. Also the contamination, as mentioned earlier, that because you are using different materials or different users, you are taking as ultra thin microtome, ultra thin sections, it will be attached to any surface, the turf or water, if you are not replacing, or edges of the knife, everywhere, the possibility, if you are not properly cleaned up. Also, the angle of knife is also important to go with the things. It is too low means it's a compression, too high is a charter. Also, there are several environmental factors. When you are taking sections, building, if there is a vibration, it will be tough to take a sections. So that to avoid, we use anti-vibration measurements. In the tubes, tennis balls or granite slabs, we used. Static electricity is one of the major causes, when you taking sections close to go with this, due to this static electricity, the sections will be flown. So that is another important, things. Wind current is also another factors. Cutting speed, when you are cutting, it should be uniform, must be fast enough that vibration does not cause uneven cutting. Also the turf, if it is low water level, then the sections will be stay behind this, wall of the knife, diamond knife. So it has to be level, it should be maintained. That is too high, it will be wetting the block. If it is too low, it is a compression. Also the block, we have to trim trapezoid so that it will be, handled easily, and sections it properly handled. So here the embedding and the sectioning, that's another important things, so when you take a sections and due to, like a water, it's floating on the surface of water, you can, already we know it's a digitalized microtome we have, then you can set at a 40 nanometer, means it should take a 40. Also, you can see under the microscope, the reflection depends thickness of sections. You will see what is the color of your section. It is determined based on that, what is the size, thickness. So we say it's silver That is the most appropriate, to visualize your sections. That is a 55 to 60 nanometer range. So the maximum, if you go with the light gold or things, then the internal structure is hard to see. So today I'm going to stop now, because I'm not feeling well. So we'll start next week, continue with this. We are on track, and still we have time to complete on time. And so if you have any questions so far. So the exam is already, 24th, I guess. Hold on. The last class, April, right? No, 23rd. So that is your exam date is 23rd, April 23rd. That is the last class. So we have two more class. Three more class. The day before the week before, we have review, so that meantime, if you are start studying, you can ask any questions, and I will tell you how to prepare the exam and everything on 16th. Or if we complete the things, I will give you in advance as well. But the exam is on April 23rd. So the exam is on online. That is exam soft. That is the one. Also, you need monitor to a prompter, a proctor for like WebEx. So you need to make sure. I hope you already had this taken online. So the exam soft and WebEx. So WebEx links I'm going to send you. I think it. So I will send you the link, new link for exam soft. For WebEx. The exam soft, the SGS office will send you the link, and you can ready for a login. 5 minutes before, I will give you the password. So meantime, if please download exam soft or everything, any software update or something, you can contact the SGS office in time advance. So be ready. So you will be, giving the password 5 minutes before the exam, so that you will log in and then you can take a exam. So meantime, if you have any questions regarding this, feel free to reach out to me. And the exam soft related questions, you can reach out to SGS office if you have any technical or software download, anything. Okay. What's your question is open note. So the exam is not open note means, Nadine? No. It's a complete exam is not open. Yeah. It is completely, you have to take on your own. You cannot compare this. So this is a final exam, and you have to study. And 50% is multiple choice, 50% is open-end questions. I hope you understand this. And already in the first class itself, I informed you all the how the exam will be. Okay. Meantime, if you have any questions in this, feel free to reach out to me. Okay. Take care. Bye.